Hello. Today we start the discussion on electric current. Now, what is a current? A current is made possible by something moving. And of course, an electric current is the motion of electric charges. Now, from your understanding of electric charges so far, tell me, what will make an electric charge move? Well, an electric charge will move when it is placed in an electric field, because a charge placed in an electric field will experience a force. If it has a net force, it will move. Now, how will you produce an electric field? Very simple. All you need is two metal plates, one charged positive and the other charged negative. Is that right? The positively charged object will be at a high potential. The negatively charged object will be at a low potential. There will be an electric field propagated from the positive to the negative. Now, if there is an electric field, tell me, what is the direction in which an electric charge would move? Motion is associated with negative charges. So a negative charge would move opposite to the direction of the field. But remember, our test charge is a positive charge. So although a positive charge will not move, you've got to assume that because it is our test charge, if you place a positive charge in an electric field, what is the direction in which it will or it is supposed to move? It is supposed to move in the direction of the electric field. So a negative charge will move opposite to the electric field. A positive charge will move in the direction of the electric field. Alright, let's now talk more about it. You have seen earlier that a positive charge placed on an electric field will experience a force and move in the direction of decreasing potential. Is that right? The direction of the electric field is the direction of decreasing potential. So a positive charge will move from a high potential point to a low potential point, and a negative charge will move from a low potential point to a high potential point. If a negatively charged metal conductor, for example, if you have a negatively charged plate connected to a positively charged plate, you establish a connection between them externally, an electric field will exist in that conductor, and that electric field will cause the electrons in that conductor to drift opposite to the direction of the electric field. Is that right? The electric field is propagated from the positive to the negative. That means the negative charges in this conductor will drift in the opposite direction. And the drift of electrons caused by the electric field is what we call an electric current. Well, since the free charges are electrons, the electrons in the conducting wire will drift from the negative end to the positive end. While the direction of the electric field is from the positive plate to the negative plate, the drift of electrons take place from the negative to the positive plate. There you are. The direction of the electric field is from positive to negative. The direction of the electron drift is from negative to the positive. The drift of electrons in this way caused by a potential difference. Remember, it is the potential difference between the two electrodes. I'm going to call these two metal plates electrodes. It is the potential difference between these two electrodes that makes it possible for an electric current to flow. That means if I can now have two electrodes. Now I think I have two electrodes here. If I can have two electrodes, now one on my left is a zinc electrode, one on my right. You see, you will probably look at this as my right hand and this my left hand. So this is a zinc electrode and this is a copper plate. They are both metal plates. If I dip this in dilute sulfuric acid, the chemical action between the metal plates and the sulfuric acid will set up a net positive charge on copper and a net negative charge on the zinc. That means I will now have a negatively charged zinc and a positively charged copper. What will happen if I connect those two externally by a conducting wire? An electric field will be set up. You see that? And a current will flow. Well, let me see if I can show that to you. Here I have a meter that will measure the potential difference between the two electrodes when I dip those two metal plates in dilute sulfuric acid. This is dilute sulfuric acid, and I have the copper plate and I have the zinc plate. Now when I dip this in dilute sulfuric acid, what will happen? The chemical action between the acid and the electrodes will give a net positive charge to copper and a net negative charge to zinc. That means you will have a positively charged copper electrode and a negatively charged zinc electrode, and this meter is called a voltmeter. What is a volt? A volt is the unit of potential difference. So this meter will measure the potential difference between these two electrodes. Well, these electrodes are now connected to the meter. Is there a potential difference between the two now? No, there is no potential difference. Well, see what happens when I dip it in the dilute sulfuric acid. There you are. It is reading 1 volt. Can you see that? It is reading 1 volt. So this simple arrangement has set up a potential difference between the copper electrode and the zinc electrode by 1 volt. What does 1 volt mean? 1 volt means 1 joule per coulomb. So this setup, the dilute sulfuric acid with these two electrodes, will make available 1 joule of energy per coulomb of charge that is driven in this circuit. Is that right? 1 joule. You see, 1 volt means 1 joule per coulomb. Volt is work done per unit charge. This will make sufficient energy, or 1 joule of energy per coulomb of charge that moves. So here we have now a system that will drive an electric current. Alright, let's develop the concept of electric current further. Now when the two electrodes that has a potential difference is connected by an external conducting wire, an electric field will propagate through the wire almost instantaneously. In fact, the electric field propagates through the wire with the speed of light as soon as the connection is established, and the electrons drift through the length of the wire. Now don't confuse with the speed of electrons with the speed of electric field. Electric field is propagated with the speed of light. It's almost instantaneous, and the electrons will then experience the force and will then drift in the opposite direction of the electric field. Now the electrons do not really move very fast. Now here I have an illustration of that concept. Now, what I just showed you, the two metal plates with the dilute sulfuric acid, is actually an electric cell, which many of you call a battery. Now, there is a difference between a cell and a battery. You see, what we really see here is an electric cell. It is really not a battery. A battery is a collection of cells. When we use more than one cell, one electric cell, it becomes a battery of cells. So colloquially, we simply call it battery. So what does the battery do in an electrical circuit? A battery produces a potential difference between two electrodes. So this battery has a positive electrode and a negative electrode. There is a potential difference between the positive and the negative electrode. And you establish an external connection by means of a conducting wire. In fact, the one I used is a conducting wire like this. This is a good conducting wire made of copper. So when you establish a connection between the positive electrode and the negative electrode by means of a good conductor, and you can see in place of the meter that I showed you in the demonstration, we have a bulb in here, an electric bulb. So look at the drift of the electrons. The electric field is propagated from the positive to the negative, and electrons drift in the opposite directions. Now, the drift of electrons is rather similar to, let me see if I can find an example. Suppose you have a group of soldiers who are in a circle, and the sergeant stands in the middle and say, "Soldiers, march." Now, what do? Each soldier will be moving like this, is that right? Now, that is analogous to the drift of electrons. The command of the sergeant is the electric field. You see, that triggers the motion. The command, as soon as the command is over, each soldier will begin to drift. In the same way, as soon as the electric field is established, each electron will begin to drift. Electric current. How do we define electric current? Now, that means if you now stay at one point of the conductor, you can see there will be a certain rate at which electrons will be crossing that particular point. So electric current in a conductor like this is the rate at which electrons flow across any section of that conductor. In other words, electric current is the rate of flow of electric charges, the rate of drift of electric charges, or rate of flow of electric charges. And current in a conductor we will represent by I. If you remember when we talked about the thermal current some time ago, we used the same letter I. So when you want to represent a current, we will use the letter I. Now, if a charge delta Q crosses a section of a conductor in a time delta T, then what is current equal to? Well, current I equal to delta Q divided by delta T. Current is the rate of flow of charge. Alright, can you look at this definition and tell me what is the unit for measuring current? Charge is measured in coulombs and time in seconds. Therefore, current will be measured in coulombs per second. Right? And that coulombs per second has